So Santosh, there is a talk by a student on shadow value evaluation today.
Yes, so there are two talks by my students. One is he's talking about like correctly rounded math libraries. This is like his TLDI work. How do you generate correctly rounded math libraries for float? And Sangeeta is going to talk about how do you do like shadow execution, like her grind FP sanitizer, but do it in parallel. Like you have a sequential program, now you have multiple cores. How do you actually do this debugging in parallel?
Yeah, this is for C family of languages.
Yeah, right now it's C.
Okay, cool. Yeah, that's just looking forward to it. Yeah.
So if you're interested, like I just shared Pavel the link to the paper. It's an FSC 2021 paper. Like if it describes it in more detail.
It's up there. I try to put these up quickly because I know people want to see them. They want to, open them in another window and open them in a new tab.
Awesome, thank you.
So we'll be starting in just a few minutes with Allison, your talk. Allison, if you want to go ahead and share the slides so we can be ready to start. Less than another minute.
You see him okay?
Yep, everything looks great. Yep, looks good. Everything seems to work.
I was just trying to move my cursor out of the way of the thing and then it switches.
Yeah, it's hard to do that in Zoom. Okay, so we should get started. It is 11 Pacific time now. So our next speaker is Allison Baker. She is a project scientist at the National Center for Atmospheric Research, and specifically in the Application, Scalability, and Performance group. And so what that means is that she works primarily with the Community Earth System module, a big climate module, and she'll be talking about that a lot in the next in this next talk. And specifically, her interests are on the high performance computing side, but also more recently data compression and verification techniques for these climate models. So Allison, please go ahead.
Thank you for the introduction. So this talk is going to be an overview of work I've been doing for the past several years with multiple collaborators. And yes, I do work at the National Center for Atmospheric Research. This is an NSF funded facility that's in Boulder, Colorado. And NCAR leads the development of the Community Earth System model. So this is a large climate code that's modeling all these different processes that are somewhat represented in this picture here in the upper left, things that are going on in the atmosphere, the ocean, the land. These are called the different components of the Earth system. And each of these components kind of does its own thing. It might have its own grid, its own time stepping routine. And so CSM then couples everything together. So this is, there's a lot going on, and that's why there's about 2 million lines of code. And yes, it is Fortran code, so yay. This code has been in development over many years. You can see the timeline below of kind of how things got started. So some of the code is like nice modern Fortran code, and some of it, I'll just nicely say, is not. There's lots of subroutines, functions, but the main thing is that, you know, this is an interdisciplinary community effort. So many people are working on it, and it's in constant development, that it's really important that we have a means of assessing the software quality so that people feel confident using it, feel confident making decisions based on simulation results. So basically, the motivation for this project and work I'm talking about is that we want to make sure that just kind of the normal things that are happening during the CSM development life cycle are not mucking up the simulation results. You can think about it this way, you know, if we run the model and it says that the ice sheet on Antarctica is melting, and then we get a new machine and we run the model again and it says, oh, actually it's going to be 10 times thicker. That's a problem. So that's basically what this work is about. So, you know, if you run a code and then you make some change and you run it again and your results are bit for bit, then, you know, that's awesome. And, you know, you're probably done. But, you know, with a code like this, we can only get bit for bit reproducible results if, you know, all these things are the same: software version, compiler, parameters. I mean, basically nothing can change. So that makes using bit for bit as a test of correctness just really impractical and restrictive, and prevents us from doing the things that we would like to do. So to kind of put it another way, the problem is, you know, we run the model, we have our output data X. Now let's say, you know, we get our new machine at NCAR, we run the model again, and now we get X tilde, and these are not bit for bit equivalent. So how do we know if the output is correct on the new machine? I mean, maybe there's a bug in the compiler, or maybe it's just different because of rounding error. And what does correct even mean? I mean, for our context, the climate scientists basically want to feel like the new simulation represents the same climate. It's not climate changing, you know, again, another vague term. They want to feel that they're going to reach the same conclusions. So it comes down to, you know, how can we assess, you know, whether the difference we see between the original and new data is significant in some, you know, climate changing way. And so what people have always done in the past is compare like really long multi-century simulations. So like we would do several scenarios on our current machine that were multiple centuries. Then with our new machine, we'd rerun the same ones. Then someone with climate expertise would compare them in a way they saw fit. It would be subjective. They would have to be experts. And so you can see this is time consuming, not only from a people standpoint, but from a computation standpoint. And so this just really wasn't practical, and we needed an automated tool. So the new approach that we took is what we call the ensemble consistency test. So climate models and, you know, weather models, these are really chaotic nonlinear systems. And what that means is, if you look at this picture I have here, if you just change the initial condition a little bit, then the trajectory that the simulation goes along will end up in a forecast that's a bit different. So an ensemble is simply a collection of simulations. So the ensemble here is all these blue lines. the initial conditions may just differ by like a round off error level perturbation. And you run them and you're going to still see this difference or natural variability, they call it. And this should be familiar to you if you've seen a forecast on TV, especially like the hurricane ones are fun. Like, you know, we think the hurricane's going to go this way, but it might go this way or this other way. And these are the chances. This is all because they've run ensembles. And so the idea then is, can we evaluate correctness in a way that they're used to thinking about it, which is with these ensembles? And what that means is that now we're not asking the question, is the new data correct? Is it climate changing? We're now asking, is the new data statistically distinguishable from the original data? This is a more objective, concrete question that we feel we can answer. And the way we do that is, here's kind of a flow chart. Obviously, I'm leaving out all the details, but we create some kind of baseline ensemble, you know, a machine, software, hardware stack we feel good about. And the next thing we have to do is quantify the variability in that. Now, the atmosphere model alone often has hundreds of output variables. So we use a tool many of you probably know called principal component analysis to describe the distribution. We then would run a few new runs on the new machine, and then we basically have a tool to say, you know, are the new statistics on these runs significantly different from what was in the ensemble, you know, yes or no? So does it pass or fail? So this is much faster. This is easier. It's in Python. You don't have to be a climate expert. Just the developers use it. And you know, how well does it work? Well, obviously, I probably wouldn't be talking about it if it didn't work. So it works pretty well. I mean, you know, we do things to the model in testing that we know should muck things up, like, you know, really increase CO2 or something. But our greater focus has been on making sure that modifications that shouldn't change the climate pass. So obviously, if, you know, I run the code today and I use 3 threads and I run it tomorrow and I use 10 threads, I seriously hope I'm not going to come to a different conclusion about global warming. So that's kind of what we're talking about. So yeah, so this test it's a kind of structured hypothesis testing. And we think that it's really useful for these numerical models where you have, you know, many output variables, like, you know, we have hundreds. It's worked really well for the climate model in practice. We've found multiple errors in our code and hardware, and we use it regularly for code verification. So we feel like this is a good way to go where you just know you can't rely on bit for bit reproducibility for correctness. So just a few more words on what we're working on now. So the big question now is, you know, what if the ECT fails? What if it says, oh, well, your results on this new machine are statistically distinguishable? So of course, your first question is, well, why did that happen? And, you know, this came about in real life with a machine we were trying out where, you know, it wasn't passing, and it took like 10 plus people and several months and lots of frustration to figure out what was causing the inconsistency. And the thing about it is it's hard for a couple reasons. One, you know, we've got just a ton of code that's in Fortran. Some of it's a bit messy. Another thing is, you know, if I run my code on a new machine and it crashes, I'm almost happy about that, because I know if it crashed, I can hook up some tool and it's going to tell me what line number and where it crashed, and I can probably figure it out. But if I just know, oh, well, it ran perfectly fine, but your output looks a little off, then I'm like, well, okay, you know, what happened? Whoops. So what we've been working on is trying to give helpful information for when it issues a fail. I mean, ideally, there's this magic tool that, you know, it issues a fail and it says, oh, go to, you know, the land module this and line of code this, and that's what the problem is. And, you know, for smaller codes that are not in Fortran, I mean, there's cool tools that can do things like this, you know, like Flit or Pliner. And so I'm not going to talk about this because I'm out of time, but basically we are trying to narrow the scope and say, okay, instead of, you know, trying to convince FLIT it could work on 2 million lines of code. We're saying, okay, we're going to try and narrow it down to like 1,000 lines of code in this module. And then maybe you can help us figure out what the issue is. So yeah, so that's about it. That was a brief overview, and I'm happy to answer more specific questions if you have some.
Great talk. Thanks so much. It's really interesting to see some of this stuff taken up to these massive scales in ways that have huge societal impact, right? Like policymakers use this output as I understand it. So we do have several questions here in the Slack. Ian had a question about determinism and whether or not there's any randomness actually used in the model. Ian, did I get that right? Or do you want to expand on that at all?
Yeah, I was just wondering if you also had to battle with run-to-run determinacy.
No, it is deterministic. There's nothing inherently random. As long as everything is exactly the same, it's repeatable. You know, unless there's something in the, that might not be true with some of the newer code that's being ported to GPUs, but like on the normal, our big NCAR, mainly CPU system, it's deterministic, yeah.
Okay.
And that actually leads to a question I was wondering about, which is, you know, we're seeing more and more accelerators come online because they have, you know, great flops per dollar, but they often sometimes also have different number formats available. And that's part of how they, you know, promise that higher value. So I'm thinking about, you know, using custom or, you know, specialized number types in like tensor cores or something. So with those GPU codes and these other things, have you thought about how the ensemble method might extend to these other hardware accelerators or targets?
Yeah, so we've actually used it to experiment with mixed precision and see if, you know, if we go into some of the physics routines and we, you know, do some of them in single precision instead of double precision, does that affect the answer too much? And we evaluate that with this ECT test. So it's been super useful for developers because, you know, it used to be as a developer, then you would have to go to a climate scientist and be like, can you look at my output and tell me? And now it's just this, you know, pass fail sort of thing. So it's been super useful for new hardware technologies.
And I guess that kind of, Pavel had this question, which I think I can summarize the right way, which is, you know, how often do rounding errors or other numerical stability challenges actually impact the output of a climate model?
Well, I mean, I guess the example I had on here that was so horrible to find was with this fuse multiply add. We find that if we compile with that on any of the machines that we've tried that have it, that we get that the result is statistically different.
Is it like, you know, we have an extra 100 years or before we're going to bake ourselves, or we have like we have like less time, or like what's the swing on that?
Well, so this might be surprising to you, but we usually do our ensembles with just like 9 time steps. We can actually tell if something's going to go off the rails.
Got it.
Very, very quickly. Things start diverging so quickly.
Because the models are so chaotic.
They're so chaotic that, you know, after like 8 or 9 time steps, if you just did a double precision perturbation on the temperature field, you'd already have, you know, hardly any matching digits after 10 time steps.
That's interesting. I guess really, that's another thing to recommend the technique is that you quickly detect this divergence.
Yeah. Yeah. When we started, we did year-long runs and we thought, oh, I wonder how short of a run we can do, because that obviously affects the cost. And we were pretty shocked actually to figure out how fast we could detect problems.
That's super cool. Well, if there's any more questions, please feel free to drop them in the Slack. Thanks again, Allison, for a great talk. It's always great to hear about the work going on at NCAR. I think with that, though, we'll turn it back over to Pavel to introduce our next speaker.
Yeah, so very cool talk, Allison. Lots of questions, even just for me in the Slack, and I'm sure other people are gonna have lots of questions too. So our next speaker is Dorra Ben Khalifa. She's a 3rd-year PhD student at the Laboratory of Mathematics and Physics at the Université of Perpignan. And she'll be telling us about her precision optimizer. It's a static tool for precision tuning of floating point code. So please go ahead.
Thank you for the introduction. So hi, everyone. Today, I'm going to present the new approach that have recently integrated in our tool POP, short for Precision Optimizer, and that offers a fast and efficient bit-level precision tuning. So let me start with some state-of-the-art. In fact, in the last 10 years, the precision tuning problem has more and more attention. So the state-of-the-art techniques can be divided into two categories. We can find dynamic tools such as Precimenus, Craft in 2013. We have ToolStoke in 2014, HIFP Tuner and Adapt in 2018, etc. And for the static tools, we found the FPTailor tool in 2015 and its extension on FP Tuner in 2017. Other tools, static tools such as DAISY in 2018 and others. And in fact, the common major drawback of all of these techniques that you can see is that they use a try and fail approach, which means that they change the data types of some variables of their program, and they run the program each time in order to evaluate the accuracy of the result. And in this talk, I will propose our tool POP, and which formulates the precision tuning problem as an integral linear problem, or ILP. So before starting, let me define some technical notations helpful to understand the ILP methods behind POP. So let's take a number, and we define the UFP of a number x, for example, is unit in the first place, which is given by this formula. Second, we define the NSB of a number x. Intuitively speaking, the NSB of a number represents the number of significant bits. And formally, if you have x hat, the approximation of x infinite precision, and if you have epsilon of x is the absolute error, then following Parker, we can bound the error on x by 2 to the power of UFP of x minus NSB of x plus 1. I continue my definitions, and now I present the ULP of a number, which is the unit in the last place, and it could be computed as the UFP of x minus its number of significant bits plus 1. Now we proceed similarly for the error of a number, which means that we define the UFP of the error as UFPE. We define also the NSB of the error, which is the number of significant bits on the computation error on X, by assuming that there is no error that arises on the constants of the programs. And in the other case, if we handle some operation between two constants, C1 and C2, whose result in X, and we have the condition that UFP of the error of C1 is greater than the UFP of the error of C2, then the number of significant bits of the error can be computed as shown. And I finish with the definition of the ULP of the error of a number, which is given by its UFP of the error minus its NSB plus 1. So in general, POP architecture is structured in 3 major steps. To start simple, in the first step, POP takes a program annotated with the user accuracy requirements. Second, POP parses this program, and after that, it performs a range analysis in order to determine the UFP of the program values. Let's take an example. Here we have an example that models the movement of a pendulum without damping. As you can see, we have a program with expressions, we have the sine function, additions, multiplication, we have the while loop. And on line 14 here, we have the statement require NSB, Y2, 20. And in fact, this statement informs POP that the user wants or requires 20 bits on a variable Y2. And in other words, NSB of Y2 is equal to 20. And after running this program, POP generates simply the same program with unique identifiers. I move now to the key step of POP, in which we formulate the precision tuning problem into an ILP problem. In fact, POP is based on a static technique which relies on a semantical modeling of the propagation of the numerical errors. In fact, by reasoning on the UFP of the program values, which I recall they are known at constant generation time thanks to range analysis, and by reasoning also on the NSB of the program values, which are unknown, except for the NSB of the result, which is given by the user, then POP is capable to generate an ILP problem, which can be optimally solved and in one shot by a classical linear solver. POP uses GLPK to solve the problem, and which complexity is polynomial. And with methods, we can find that our precision tuning method can be solvable in polynomial time. At this stage, I need to shed the light that in our ILP formulation, we are pessimistic on the carry bit that can occur on our results, which means that if we have exceed the carry bit function of our programs, we add at each time or at each operation 1 bit on the result of our program. If we take our running example of the pendulum again, and now if we concentrate or focus on only the line 6, here we have assignment, an addition, and a multiplication. Then POP for this line generates 7 constraints. We have 2 constraints for the addition, followed by 2 other constraints for the multiplication. We have 1 constraint for the assignment, and the 2 last constraints, which are given in red, are for the Xi function, which are over-approximated to 1, respectively for the multiplication and the addition. I need to insist that POP generates such constraints for all the statements of the program, and currently POP supports the conditionals, the while loop, the for loop, arrays, matrices, square roots, and trigonomic functions, etc. And in terms of complexity, our constraints generated are still linear in the size of the program analyzed. And as a solution of, or after resolution of our system, we found here the tuned pendulum program with the new optimized precisions that are mentioned in blue. And we can find that the 20 bits required on Y2 variable are correctly propagated from the bottom of the program and until the top, giving a total of 861 bits at bit level instead of more than 2,300 bits for the original program, by assuming that the original program, in the original program, all the variables are in double precision. So the question that we ask now is how to be more precise or how to do much better if we are less pessimistic on the carry bit propagations. And this is the subject of the 3rd step of POP analysis. In fact, after an observation, we found that this carry bit or this over approximation of carry bits is very expensive when you have large codes with a lot of computations, and the errors are considerable. For that purpose, we propose the following optimization. If we have a simple addition between 2 numbers C1 and C2 whose result is X, then by comparing if the ULP of one of the operands is greater than the UFP of the others, then in this case, the errors cannot overlap and there is no need to add an additional bit. Otherwise, if the 2 errors overlap, in this case only we preserve the carry bit on the results. In fact, this new optimization has an equivalent mathematical definition of function Xi, which is given with min and max operators. And in order to compute this new Xi function, we need to estimate the number of significant bits of the errors of our numbers. And as a conclusion, the problem is no longer ILP formulation. And in order to solve our problem, we have used the policy iteration technique, which is usually used to solve nonlinear fixed point equations. And as a result, we need to add a supplementary constraint to our initial system of constraints, as you can see here, the system C2, in order to estimate the new quantities NSBE of the values. And these constraints actually will be added to the former system of constraints that was generated in the ILP moment, in which the only difference is to activate these new optimized XC function instead of its over approximation in the ILP method. And as a result, we found a more precise precisions, if you can say, by the PI method or the policy iteration methods. In fact, as you can see here, what remains in blue is the same number of bits as we have found with the ILP methods. And what I did here, I mentioned in orange, are the variables for which we gain some bits of precisions, forming a total of 843 bits at bit level with the policy iteration methods, then or instead of 861 bits that we have seen with the ILP method. So I will show some experiments of our paper, and I will focus on the comparison that we have made with two state-of-the-arts. Our tool, POP, which was published its first version on 2019, and which used the SMT Solver Z3, and the prior state-of-the-art Precimonus as a dynamic tool. And in order to make this comparison possible, we were in the obligation to adjust some criteria between POP and Precimonus because of the two tools don't integrate the same techniques. The first criteria is that POP optimizes much more precision than Precimonus, and in these experiments we only consider the variables that were optimized by Precimonus. And as second criteria is that in Precimonus the error thresholds are expressed in base 10, whereas in POP we express our error thresholds in base 2. And in the experiments, we do as Precimonus does, that all our thresholds are in base 10. We take here two benchmarks, the Erg-Length program and the Simpson program, which are Precimonus benchmarks. And we take two POP benchmarks, a program that implements a rotation matrix and the accelerometer program. And if we can see for an error threshold of 10 to the power minus 4, we have POP ILP that saves more bits than the other tools. We have, it saves 2,464 bits in a time nearly 2 seconds, whereas POP SMT saves only nearly 1,500 bits in 5 seconds. And the slowest tool was Precimonus with only 576 bits in 3 minutes. And this same behavior can be seen for the other thresholds, 10 to the power of minus 6, etc. Also for the Simpson program, we have POP with its method ILP that optimizes more bits than the previous edition of POP and Precimonus. Whereas here in the rotation program, we have a POP that wins only for an error threshold of 10 to the negative minus 4, whereas Precimonus wins and saves more bits for the other thresholds. An explication can be given either we are disadvantageous because we only take the variables of Precimonus, but if we keep all the variables that are optimized initially by POP, we can do better. And finally, for the accelerometer program, POP optimizes well and saves more number of bits than the other tools, whereas Precimonus fails to tune this program. So as a conclusion, what I have proposed here is the new approach for precision tuning for POP. The first variant is that you use a pure ILP with an over-approximation of the carry bit functions. The second method is we use a more precise query bit function that are solved with the policy iteration methods. Of course, as a limitation, we can be limited in the size of the program accepted by the solver. And several future directions can be proposed. We can reduce the number of variables that we generate by assigning the same precision to the whole piece of code. For example, the same expression will have the same variable. Also, our technique, we believe that it's adaptable for GNNs. And also, we are interested in future work to code synthesizers for fixed point arithmetic. I finish with the main references of POP for its previous and current edition. And I thank you all for your attention.
Very nice talk. I think in the interest of time, we are going to go ahead and keep progressing to the next talk. However, I will note there was a nice and quite active discussion. I think Dorra and Mathieu sort of tag teamed on this one, and that worked out really well. So Dorra, you can see you know, what Mathieu was saying in the Slack. But I think we'll go ahead and go on to the next talk.
Okay.
Yeah, thank you. Really great. Okay, so yeah, we're like Zach said, we got it. We're gonna keep moving just to stick to the schedule. And so our next talk is from Theo Drane. So Theo runs a mathematical hardware group inside Intel's graphics division. And he's got a long history in various kinds of like mathematical hardware. He worked on data path optimization at Cadence, at Imagination Technologies on the GPU team. And well, now he's at Intel working on optimizing their mathematical hardware. So please, Theo.
Thanks, Pavel. So first of all, thanks to Pavel and Zach for building the community. And hopefully what I can do in my talk is contribute a hardware perspective. And also I won't be selling solutions, I'll be selling problems, which I think could be rather entertaining. So I work on mathematical hardware and I'm very easily bored. So what makes mathematical hardware interesting is if it's constrained in all of these four senses. So I want to work on a hardware design that is mostly mathematics. I want different algorithms in that hardware. It has to be constrained in both power, area, and speed. And I also want something that is evolving. And I've worked on various different disciplines, but essentially I found my solution in GPUs. So if you obviously dive into GPUs, are they hardware constrained? Completely. For all these different applications, you know, we have notions of photorealistic rendering of 3D geometry. We have high performance computing. There are obviously mobile GPU cases. All of these things translate into speed, latency, area, and power constraints. These are definitely diverse in their algorithms. So where, of course, we have HPC requirements, things like OpenCL that must be IEEE, fully IEEE compliant. We have, you know, the new cowboy. We have machine learning. What's the hardware we need for this? But we also have other very crucial bespoke hardware requirements for things like texturing and ray tracing and geometry computation. And then the other really nice thing is these things are clearly evolving. There's a whole zoo of different GPUs that are being created. So we have all these different styles of GPUs, sizes, and they have this diverse set. So this is why I focus on GPU mathematics in terms of hardware creation. And the other great thing, of course, is because it's hardware design, I get to do formal verification. The cost of bugs is very high. So that's the domain. But let me tell you, first of all, what hardware design isn't. So there are things out there that allow you to immediately jump from some kind of system C or C++ model directly to a hardware design. And that's typically at an integer operation level. And then you can do logic, what's called logic synthesis to generate your logic gates. But typically what this looks like, of course, is you would be hamstrung by the data types. And so there's a small number of basic number formats we could play with. Obviously, they're going to be IEEE compliant. And when you do high-level synthesis, it basically just synthesizes the atomics. And the HDL it produces is essentially integer level. But we don't do any of this. Because of GPUs, because they're so interesting, we actually have hundreds of different number formats, and we routinely deviate from the IEEE standard. We categorically don't atomically synthesize. We don't make atomics. We will routinely share different data types. I will make hardware that shares integer, fixed point, and floating point. And do I make integer level RTL hardware design? Definitely not. I will go down into a gate level RTL. So the flow at the top isn't what we do at all. And this is really what goes on. We take some kind of system model, and then there's all these lovely manual steps. And this is particularly true for GPUs because of all the constraints that I described. For other types of hardware design, you can do high-level synthesis, but that's not what we do. And I deliberately, of course, it's nice to place yourself in harm's way. How hard does this need to be? So essentially, this is the real design flow. So that's how this actually works. I will then show eventually that's not how this works at all. But let me give you something simple. And it's been really nice to hear, this topic of precision tuning is just wonderful. So in the past, it's lovely to hear about some of these tools, singles, doubles, halves, this kind of thing. But obviously there's now this emergence, custom floating point precisions. And obviously in a GPU, by the way, we might use at least 45 different precisions of floating point easily. Anyway, so here's a simple case that's basically being kind of discussed in some ways. So if we did have a bespoke piece of floating point hardware for something very error tolerant like texture, then we would have some kind of data flow graph, and we can literally ask questions, how do I determine the precisions? And so that's a really interesting trade-off. That's an accuracy hardware trade-off. And this, obviously, it's been lovely to plug into the FB-Bent community. There are tools that can help me analyze. And to solve this problem, we can, of course, bring in some of our hardware tools. So there's this really interesting question, how do we bring these tools together? But this is actually the simplest case I could think of. It's not actually what we care about. So here's something slightly less simple, but it's still ridiculously simple. So just as a small example, I could take off the textbook shelf an approach at doing double precision reciprocal. And I can use Newton-Raphson iterations, and I can structure all this lovely thing with different precisions, and I have to check that the extended exponent, all these lovely things. But the really cool thing about hardware design is having something that works and provably works is great, but it's just the beginning. Because what we're actually doing is we will be pushed as we should be, and that every single gate that we create matters. And what does that mean in this setting? Well, it means this. So in the middle of this essentially operation list, I have an FMA, but the questions are going to be, I actually need to know the exact specification for the FMA. I need to know the exact input domain. And it's been nice to see some of the talks discuss input domain. But the really cool thing here is I need to know exactly what the input domain is, because then I can build bespoke hardware to do just that. Or even if I'm not building bespoke hardware, I can do power optimization and ignore certain bits of the input. And so I really need to know the exact specification. And the tighter that specification is, the more power I can save. So even if it's not about building bespoke hardware, there's still this power question. So I really actually need completely tight specifications for operations in the middle of some of these data flow graphs that we have. And then, of course, we have the general lovely question. I mean, this overall approach, while the output is, we know exactly what the bit accurate output's going to be, we clearly have these freedoms inside the design. How accurate should the reciprocal value be in the first place? And all of this has power consequences for hardware design. So these are actually the questions we ask, not just is it correct, which is relatively easy, but actually what is the best of the best from a hardware design perspective? And to really reverse the direction of this discussion, I'm going to point out something very entertaining. We are the people who build floating point operations. we can build anything we like. Different rounding modes, round to nearest even, round to nearest odd, some crazy thing you can cook up. So we are the people that know how much smaller something can be. So we know that round towards 0 is 25% smaller than round to nearest even. But we also know that I can make something that's faithfully rounded to 1 odd 45% smaller. These are very non-trivial things. At a very high level, they may not be very important per se, but from a hardware perspective, we need to know this. And to really throw a curveball that hopefully you'll find entertaining, I can make a floating point multiplier even smaller than this if I sacrifice commutativity. People find this hilariously entertaining, and why on earth would you do this? But as we're hardware designers, we can do this. If you want to sacrifice monotonicity, commutativity, associativity, we can do things with that freedom. So that's really what goes on in hardware design. So that's now a less simple case. But now I'll just finish with the real case. What are we really doing? And in the real case, we have to choose our algorithms. We can choose our number formats. We can choose between different hardware, fixed point, floating point. We can logarithmic, the list goes on. And then we can ask components. We can actually build things that people would love to have. We can build a custom Euclidean norm if we want to. Then we choose precisions. Then we can discuss the accuracy of every operation, and we can build anything we like. And then only then do we start doing hardware optimization. So all of that just determines the bit accuracy of what we're doing. And then the other subtlety I mentioned earlier, if we know properties of the inputs, we can make cheaper hardware still. So we remove redundancy. If we know that part of the actual hardware will never be used, we're going to delete those gates. And obviously the challenge linked with all of this is then formally verifying throughout. So hopefully that gives you a flavor of the multitude of choices. And it was lovely to see what Allison did, the entire stack of things that affect the climate models. Here is the stack that we deal with in hardware design. Okay, and so hopefully one of the things that's not surprising, at the beginning of the talk, I mentioned this high-level synthesis thing where you start with your C++. And basically it's a type of tyranny, because obviously what we do as hardware designers, we do this. We know what makes good hardware, and we're essentially doing that back pressure on the algorithm design. And so essentially that's what my group does. It's basically a co-design group. And it's really interesting to see the various disciplines in FP Bench, because clearly, what we're looking at here is the whole combination of formal verification, algorithm design, hardware optimization. It is clearly interdisciplinary. So hopefully that gives a flavor into the hardware questions that hopefully augments the rest of the flow of the talks.
Excellent. Thank you so much, Theo. This is great. As soon as you said non-commutative multiplication, the Slack just blew up. I think everyone's sort of faces melted a little bit there. I think there's a lot of conversation to continue to have there, but maybe one quick question before we jump to the next talk. Can you give an intuition for why that's a win?
Yes. Let me explain. You can imagine certain algorithms that may be inherently commutative. You might do an encoding to one of them, but not the other. So there's an inherent asymmetry in certain algorithms. So if your algorithm actually is commutative, but under the hood, you do something interesting, any kind of localized encoding scheme or essentially you could say different number formats.
Right.
So imagine you have two numbers of a particular input format, you change the number format of one and not the other, you shouldn't be surprised that you can actually make non-commutative things. Now, I'm afraid, of course, I'm not allowed to build these things, but I just wanted to throw it in because this is essentially the back pressure that we learn by doing hardware design. I will be prevented from doing this.
Denard scaling, unless Denard scaling comes back, I suspect within the next decade they're gonna let you loose, and and see what happens. But yeah, so folks, please keep the discussion going in the Slack. This is super interesting stuff, and my mind is blown at how much is sort of left on the floor if we want to keep things like communicative. That's really quite surprising. But I think we will, for schedule reasons, go ahead and bounce to the next talk. Pavel, if you want to do the
yeah, absolutely. So our next speaker is Clothilde. Oh man, the last name is going to be hard, so I'm asking for forgiveness ahead of time. Clothilde Jeangoudoux. That's my guess. Anyway, Clothilde is a postdoc at the Max Planck Institute for Software Systems. But the work that she's going to be presenting here, she actually started doing during a PhD in the aeronautics industry. So looking at safety critical systems and how to test them well. So Clothilde, please.
Thank you very much for the introduction. And my name is Jeangoudoux, but I know that French is difficult with the English-speaking people, so that's fine. So hi, everyone, and thank you for coming to my talk. Today, I will present the work I did during my PhD with Christoph Lothar and later during my postdoc with Eva Daronova. So let's start with an example. We are given the specification of the extracted airflow of a helicopter engine. The input X's are defined over the rails in continuous ranges. This critical system is computed with finite precision, like for example, in this code, where the reals are representing with floating point numbers. There might be some rounding errors while computing a real valued specification with finite precision. That's why the specification is not defined exactly over the reals, but with a relative error epsilon. So now the specification defines a range of possible values, while the code computes a single output. Hence, the specification is not the code. We want to test if this code is compliant to this specification. We could simply use random testing, but this technique is forbidden for the certification of safety critical systems. Moreover, in this particular case, to generate tests, we only have access to the specification. The code is not actually available. In this context, we want tests that target specific bugs. To do so, there exists a technique called mutation testing that does exactly that. It's a white box technique that injects faults into the system on the test. For example, let us take this specification. A mutant is a modified version of the specification. We can easily define a test by fixing the values of the input variables and compute the expected output of the specification, R is equal to 2. When evaluating this over the mutants, we get the output Rm is equal to 4. R and Rm are not equal. The test successfully uncovered the faulty mutants. We say that the mutant is killed. Mutation testing is an effective way to assess the quality of a test set with the test adequacy. It's a value between 0 and 1, 0 meaning no mutant was killed, and 1, every mutant were killed. Mutation testing also allows for test generation. So given an input program specification, the first step is to generate a set of mutants representing common mistakes or bugs. With initially the initial test set, which is empty. No mutants are killed by the evaluation of the mutants with the test oracle. Then we go to the second step, which is the automatic test generation that targets those mutants. And we do it iteratively until all mutants are killed. However, this algorithm is not so simple when it comes to using finite precision arithmetic. So here over the rails, we can define the valid range in green and the invalid range of the specification and also those ranges of the mutants, and we can compare them. But our first challenge is to define a finite precision test oracle that will reliably compute those ranges, even in the presence of rounding errors. The second challenge will then be to adapt the test generation algorithm to this new test oracle and numerical specification. And finally, our goal is to target accuracy errors that may occur in the implementation of numerical specifications. We will then need a new accuracy mutation to target those specific errors. Our tool Magneto extends classical mutation testing as follows. We first represent the input specification as interval constraints. We then we use this representation to create mutants targeting classical implementation bugs and also round-off errors. We create a new test oracle using interval arithmetic to reliably assess if a mutant is killed or not. We also introduce the uncertain verdict when the test is not accurate enough to reliably kill a mutant. And finally, we use interval constraint solving to generate new tests to kill the surviving mutants. I will now present each steps of this algorithm, starting with the representation of the input specification. A constraint satisfaction problem is defined first by a set of variables, here the input axis and epsilon for the relative accuracy, then a set of constraints define the range of the valid outputs, and finally a set of input domains of each variables. Here the interval domain of epsilon in orange on the slide is particularly important for creating mutants targeting accuracy errors. We can now apply mutations to the original specification. The mutations are the rules allowing to create a set of mutants. We use the following mutations traditionally used in mutation testing. For example, the constant mutation, which changes the value of a constant here 4 instead of 5. The other mutations swap, add, or remove variables or operations in a constraint. We define the new accuracy mutation that targets round-off errors by decreasing the precision of the specification, which means increasing the range of epsilon. So here we have a new epsilon mutated with a bigger range than the original epsilon. Now that we have a representation for specification and a set of mutants, the challenge is to know if a test can kill those mutants. For real value specifications and mutants, computing the valid and invalid ranges is sufficient. However, in practice, we also need to consider the finite precision of the test oracle implementation, which leads to rounding errors shown here with the new error delta, especially if computing transcendental functions. We use interval arithmetic to take rounding errors into account, which creates a new range where we cannot say for sure if the value is valid or invalid, and we call it the uncertain range. By using interval arithmetic, we can reliably compute the valid and invalid ranges and use them to compute the verdict of the test. So we say that the mutant lives or the verdict is okay if the valid range of the mutant is comprised in the valid range of the specification. The mutant is killed or the verdict is KO when the valid range of the specification coincides with the invalid range of the mutant. And in any other configurations, the verdict is uncertain. We then need a beta test to reliably kill the mutant. For the accuracy mutation, things are not so simple. Since we decrease the accuracy, the valid range of the mutant will always be at least as big as the valid range of the specification. So we see here that the valid range of the mutant overlaps with the uncertain range of the specification. We say that the verdict is uncertain. And even when the valid range of the mutant and the invalid range of the specification overlaps, then we cannot say for sure that we will generate tests that are guaranteed to capture accuracy errors without knowledge of the actual code. So what we aim at is identify test inputs for which the overlap between the valid range of the mutant and the invalid range of the specification is big, which means we only keep test inputs that cause numerical instability. In general, finding those test inputs to kill the accuracy mutants is difficult, especially with random testing. The main test generation algorithm also uses valid and invalid ranges comparison. In the general case, we define a constraint that will guarantee that the generated test will be in the valid range of the specification and in the invalid range of the mutant. In addition, interval constraint solving guarantees that the solution will not be in the uncertain range of the mutant. Likewise, the constraints in the generating tests for the accuracy mutation defines the invalid range of the specification and the valid range of the mutant. We tested our approach on 69 benchmarks from the FP benchmark suits, which I guess you all know about. We use particularly benchmarks composed of straight line codes with in average 8 operations, and we generated in average 179 mutants for those benchmarks. Even though random testing is not eligible for the test generation of safety critical systems, there is, to our knowledge, no other tool to use as a baseline comparison to Magneto. So here, black box testing amounts to randomly generating test inputs and only keeping tests that increase the adequacy score of a benchmark. For fairness of comparison, we let black box testing run over the same amount of time that it took Magneto to finish its execution. The median execution time of 20 seconds showed that even with some benchmarks taking up to 18 minutes to evaluate, most evaluations were not too time consuming. On this graph, we compare the adequacy score of Magneto on the x-axis and black box on the y-axis. We see that Magneto always produces better adequacy scores than black box. They both killed between 70 and 100% of the mutants for each benchmark. However, the average adequacy score of Magneto over all benchmarks is not that high compared to black box. So here we have 88% instead of 85%. And we can better understand these results by looking at the adequacy score of the old benchmarks per mutations. We see here that Magneto performs very well on the accuracy and the bounce mutations, but they only represent 7% of the total number of mutants. Even if there are not a lot of mutants for those mutations, they are the most interesting mutations for us because the bounce mutation changes the input domains by several of the magnitude of epsilon. That means that there are a few test inputs that can detect that mutation. And while black box struggles to kill those mutants, Magneto consistently finds tests for those low occurrence test inputs. And similarly, Magneto performs well at finding test inputs to kill the accuracy mutants, that is the test with high numerical instability. In summary, we proposed an adaptation of mutation testing for numerical specifications. We first defined a reliable test oracle using interval arithmetic, which we used in our mutation testing-based algorithm for test generation from a numerical specification. We have shown that this approach is effective to catch common programming bugs and also accuracy errors. In the paper that we published to ISTAR, which is a conference taking place right now, we also go more in depth into interval constraint solving and the problem of equivalent mutants. I would encourage you to read the paper to learn more about that and to see our tool Magneto available on GitHub. Thank you for your attention, and I'm happy to take questions.
This is super cool. We have several mutation testing researchers at the University of Washington, where I am, and I always ask, like, what about floating point? And they always say, we don't know. So it's really neat to see people, to see this work bringing the power of mutation testing to the numerics world. Got a few questions here in the Slack. Actually, Ganesh, I don't know, do you want to ask your question live or?
Yeah, sure. Yeah. Nice talk, Claudio. Yeah, wondering how you would compare your approach with Verificarlo, which also does a value space Monte Carlo mutation in a sense. So do you get more insights using your methods or using a statistical method like Verificarlo?
The problem with statistical methods, I guess, is that they use some kind of randomness. So the first approach for me, the first constraint was you cannot use any randomness for safety critical system for the certification of those systems. And I didn't think about comparing our approach to Verificarlo, but so I don't know what would be the results.
Yeah, thanks.
And I think Chandra also had a question, possibly.
Yeah, so I had a couple of questions. So my first question was, so you said in the beginning that the code for the benchmarks was not publicly available, right? So then how do you mutate them, the source code for?
So the code is available for the benchmarks. So the problem is for safety critical systems, there is the specification, which usually is like where I did my PhD, it was in text in French. And then you have the code in some other formats. And the workflow is that you cannot look at the code to generate the tests to verify the code. because if you use the code to generate the tests, then are you really verifying the code or not?
Yeah.
So that's the workflow for certification. So I was not able to look at the code, and I could not also verify if my test actually worked on some code, because I would have to have some faulty code to test if that was useful test set.
Cool. Thanks.
Thanks so much for a great talk. And there's more questions in the Slack, and if folks have additional ideas, we should definitely continue the discussion there. But I think we'll hand things back to our fearless leader at the close of the session here.
All right, thanks, Zach. Yeah, so we're at the end of our third session, and we have our 2-hour-long break for lunch. It may not be lunchtime where you are, but we hope you'll come back in 2 hours. We've got 2 more sessions after the long break, and I think they're going to be very exciting. There's a lot of really great talks there. So I hope to see you in 2 hours then. For this lunch break, I will be closing out this Zoom. So we can't really continue a discussion here, but I'll try to reopen it about 15-20 minutes before the next session starts, so that you can sort of, come back in and not miss any part of it. And of course, there's some very dynamic discussions going on in the various question threads for the different talks. So that of course can continue. So I'll see you all in 2 hours for our last 2 sessions and for some really great talks coming up. See ya.